Hello, I'm Mr. Baker. This is going to be a pretty short lesson video, but we're covering the fourth lesson in my unit on evolution. And we're going to talk about patterns that can be observed when there's no evolution occurring and kind of how scientists tell if evolution is actually occurring. Right? This is more of a math-based lesson, and I'm just not equipped to teach that virtually, so I'm going to probably either add some cards to this video or add some links in the description. Maybe I'll just host those videos in the playlist, not re-upload them, but link to the original authors, right? But we're going to talk about something called the Hardy Weinberg equilibrium, right? The Hardy Weinberg equilibrium is something that is used to tell when evolution is occurring. That's a when as in if it is occurring or if it isn't occurring, not a time period, right? So allele frequency will remain constant, and therefore there's no genetic variation and no evolution occurring if these five things are happening, right? So these are the five things you would need to know if I were to ask you, or someone else would ask you, if Hardy-Weinberg equilibrium is true, right? So there has to be a large population. That will mean that any genetic drift, remember back in lesson 2 we talked about genetic drift, is happening or not. Large population means genetic drift doesn't really account for any big differences. Genetic drift only really causes changes in smaller populations. If there's no immigration into the population or immigration out of the population, that means that the allele frequencies are going to stay constant because there's no big influx or loss of alleles. Mating has to be random so that preferential passing down of traits isn't occurring, like, say, from differing mating dances or from something like natural selection, right? Because if natural selection is occurring, then evolution is definitely occurring. And if there's random mutations occurring, that can also influence evolution, right? It introduces variance, right? So mutations can't be happening, right? So I'm going to just briefly talk about this equations, or these two equations really, and then I'm going to hope that you go watch somebody else that will teach you the math for this. In my class, we're going to go over the math in class quite a few times, right? So these are the two equations for Hardy-Weinberg, and you're going to use both of them to solve for different frequencies of alleles and for phenotypes, all right? So most of the time in my class, I'm going to keep these word problems pretty simple. I know you don't like word problems. Most people don't, all right? But we're going to keep these two equations. For my class, you don't even have to memorize these. I'll have them written on the board whenever we need them, right? Because in real life, you can just go look them up, right? Simple Google will find those answers. All right, so most of the time in my class, we're going to start with Q squared, the frequency of the homozygous recessive genotype. So we're going to look for those homozygous recessive individuals in the word problem. You might not be given the number of homozygous recessive, though. Maybe you're given the frequency of homozygous dominance instead, P squared, right? Or you're given, I will never do this, but somebody else might in a higher level math class or higher level biology class give you the frequency of heterozygotes, right? That's the hardest way to start this equation, right? Q squared or P squared are much easier to start from, right? So if you are given the homozygous dominant phenotype or the homozygous recessive phenotype, if you just square root it, right? P squared square rooted gives you P. Q squared square rooted gives you Q, right? And your phone calculator can do that. Remember, if you don't see that button, turn it horizontal, right? Landscape mode, let that happen. The calculator will probably expand and you'll get the square root key, right? That gives you either P or Q, and you can use the other equation, the one I've typed there at the bottom, P plus Q equals 1. Those are for phenotypic ratios, but because both of these are related equations, we can just work through both of them, right? So once we've got P or Q, we can plug that value into its variable in our phenotypic equation. P plus Q equals 1. Do a little bit of algebra, and then we'll get the other variable. So if we started with P, we would now have Q. If we started with Q, we would now have P. Now we've got both P and Q, and we can solve for any other number that we need here, right? we can solve for each variable. Like I said, we'll go over these in class, and I'll probably be just hosting other people's videos on walking through the math. Remember, if we have two populations, we can find their frequencies with the Hardy Weinberg equations. And if the frequencies match between the two populations, then no evolution is occurring. If the frequencies don't match, then evolution is occurring, right? So we can check if evolution is occurring or not using this method.